So far we have understood some basics of linear algebra, and we have seen the idea of vector as we generalize in linear algebra. Now here in this lecture we will connect this idea of vector with linear equations. We will show you that the linear equations are coming from vector. So let us see. Let us take the idea of a machine. The machine takes an input x and it gives an output of f of x. Now, this kind of machine in mathematics are called function or operator. Now, if I give an input x1 to this machine, the machine will give me an output of f of x1. Similarly, if I give an input of x2 to the machine will give me an output of f of x2. Now if I give the input of x1 plus x2 in the machine will give me an output of f of x1 plus x2. If I give an input of ax1 to the machine will give me an output of f of ax1. Here a is a constant. Now, this kind of machine we call them linear machine if this f of x1 plus x2 is equal to f of x1 plus f of x2 and f of ax1 is equal to f of x1 for a being a constant. You can see that in general we cannot say that it is true f of x1 plus x2 give me f of x1 plus x2, f of x1 gives fx1, x2 gives f of x2. So f of x1 plus x2 will be f of x1 plus f of x2. This is not obvious and we have to see it. All machines are not linear. So this kind of machine in mathematics we call them linear operator. The operators, of course, which are not linear, they are non-linear. So if certain machine they violate this principle, then they will be non-linear. So let us see that what do we mean by all these abstract ideas. Let's take a machine which will give me fx that is equal to 2 times x. So if I give the machine an input of x, machine will give me back 2 times x. In this machine, if I give an input of x1, machine will give me back twice x1. If I give x2, machine will give me back twice x2. So you see that f of x1 plus x2 is equal to 2x1 plus 2x2. So 2 of x1 plus x2. And you can clearly see that it is equal to f of x1, that is 2x1 plus f of x2. So this is actually obeying the first principle of linearity. Similarly, you can see that f of twice x1 equal to, of course, 4x1, which is 2 multiplied by 2x1, and 2x1 is f of x1, which means that f of 2x1 is equal to 2 multiplied by f of x1. So overall, this fx equals 2x, this is a linear machine. So this is linear. Fx is equals 2x is a linear sort of relation. Now we check one more. Another type of machine where fx is x square. I give an input x, the machine will give me the output of its square. So if I take f of x1, it gives me back x1 square. For x2, it gives me back x2 square. So x1 plus x2 will give me back x1 plus x2 square. Well, f of x1 plus f of x2 is only x1 square plus x2 square. I know that x1 plus x2 square is, as we have learned in our school, that would be x1 square plus x2 square plus twice x1 x2. So this f of x1 plus x2 is not equal to f of x1 plus f of x2. Therefore, this machine which gives me this f x equals x square is a nonlinear machine, or this kind of operator is nonlinear operator. This is an important concept in mathematics, and in particular in linear algebra. We have to be very familiar about this. Now, if fx is linear and fx equals c, then this kind of an equation where x is the unknown, we call this linear equation. C is, of course, we have to know C. C cannot be something related to x. So C is a constant, we know it. So this is a linear equation as long as fx is linear. And of course, equations that are not linear, we call them non-linear equations. So in short, in linear equation like this 2x equals c, you can see that unknowns are not multiplied, but here this is non-linear. So if I take x square equals c, unknown is multiplied with another unknown. So this is a non-linear equation. Now we come to linear algebraic equation. So in algebraic equation with one unknown x, we generally write them as in terms of a polynomial. The polynomial is this an x to the power n, an minus 1, x to the power n minus 1, all the way up to a1x plus a naught equals 0. This is a polynomial. So in a general algebraic equation, we write in this way. We can also write in a short notation, that is summation of I equals 0 to n, ai x to the power I, a0 x to the power 0 will be simply a0, then a1 x to the power 1 will be a1x, etc., all the way up to an x to the power n. In this case, the n must be a positive integer, and all these a's are constants, and we know them beforehand. This equation, to make it linear, we have to have from a2 to an everything should be 0, because linear equation cannot have this x square, x cube, etc. Therefore, from a2 to an everything should be 0. And of course, if a1 is also 0, then this becomes a trivial case. So we assume a1 is not equal to 0. So my equation is a1x plus a naught. So that is a linear equation. And we will talk more about linear equation now that we have formally understood what is linear equation. Now a linear algebraic equation with one unknown is thus have the form of a1x plus a naught equals 0 and a1 not equal to 0. Then if a1 not equal to 0, there is no unknown. So we are not interested of that kind of relation. So this is our linear algebraic equation of one unknown. Linearity, of course, applies to differential integral equations as well, using the same type of property, assuming same type of machine, and you can try that as your exercise. Solution of one linear equation with one unknown is trivial, and we are not really interested about that so much. In linear algebra, we talk about a set of large number of equations with large number of unknowns. So in general, we have m equations and n unknowns. Although we solve usually cases where number of equations are equal to number of unknowns, but in general in linear algebra deals with cases where this m and n may not be equal. In general, of course, m and n obviously greater than 1, otherwise it becomes a trivial case of one linear equation, one unknown. Most of the equation, in fact, at least one equation here in this set must contain more than one unknown, then only it becomes something of our real interest. In general, the form is like this. I have this, all these a's are known, a, I, j's are known, and a11 x1, a12 x2 up to a1 and xn equals b1, a21 x1 a2 to x2, a2n xn equals b2, etc., etc. am1 x1, am2 x2, amn xn equals bm. So we have m equation, and each equation has x1 to xn, this n unknown. However, some of these a's may be 0, so it is not necessary that every equation will have n unknown. But in general case, every equation may have n unknowns, and we have m number of equations. These are the cases we are really interested about in linear algebra, and some cases like this we are going to solve. The equation, of course, you can write in a short form as the summation j equals 1 to n aij xj for bi, where I goes 1 to m. So each I gives an equation. I equals 1 is equation 1, I equals 2 is equation 2, etc., etc. This is a summation that appears in every equation. Linear algebra can also be understood as a linear combination of unknown. So what is linear combination? We have already discussed a little bit of linear combination. So let us say linear combination of x and y. Linear equations can also be expressed as linear combinations of unknown. What is linear combination? So let us say two mathematical entities x and y. Their linear combinations will be ax plus by, where a and b are simply numbers and they are known to us. Now, clearly, linear equations such as here this 3x plus 2y equals 5, that is a linear combination of this unknown x and y. The idea here that we are trying to understand is that in a set of linear equation, one of these equation can be replaced by a linear combination of equations, and at the end the x and y will remain same. So this is a very important idea, and our first algorithm of solving linear equation is exactly based on this. So let us see this two equation, 3x plus 2y equals 5, 4x plus 5y equals 9. In this equation, what I do is that I take equation 1, multiply with this to 1 and 0 to equation 2 and make that my new equation 1. So essentially what I mean that I do not make any change in equation 1. It remains just the same. However, equation 2 is 1 of equation 2 plus 1 of equation 1. That means this is just adding equation 1 and 2. So 3 plus 4, 7, 2 plus 5, 7. So this is just equation 1 plus equation 2 I have added. If I solve this set, whatever the value of x and y I'll get, if I solve this set, I should get the same value of x and y. This is the key. This may sound trivial, but this is the key of solving large number of linear equations that we'll see shortly in upcoming lectures. Similarly here, as I go from here to here, I see that I do nothing. This is same, the equation 2. Equation 1 is equation 1 and equation 2 are added together. So 7 plus 3, 10, 7 plus 2, 9. So this is 1 plus 2 added. I have a new equation. Here you see that from here to here, this is same. We do nothing for equation 1. As I go from here to here, the second equation, I divide by 7, or we can say that I multiply 1 by 7. So x plus y equals 2. Once again, the result of xy from here will be same as result of xy here, same as here and here. So all these equations, we call them equivalent because they will give us the same xy. And this kind of equivalent system we can generate by making linear combination of the original equations. This is a very important idea and we will use it quite a bit. In the same way, linear equations can be seen as linear combination of vectors. So for example here, see that these two equations 3x plus 2y equals 5, 4x plus 5y equals 9. we can write this as x multiplied by vector 3, 4, y multiplied by vector 2, 5 equals vector 5, 9. Here this t actually a symbol which we call transpose, and writing this vector 3, 4 without this t is something we call row vector. That is, if I write 3, 4 like a column, we call that column vector. The transpose of row vector is a column vector, so 3, 4 t is a column vector, and 3, 4 here is a row vector. Usually most vectors are indicated in column by default. If we don't know it's a row vector or column vector, then it is a column vector. So all vectors are treated as column, and we can write column vector like this, like a column, this 3, 4, or we can write 3, 4 t. So here x 3, 4 t, y 2, 5 t equals 5, 9 t. This is the way to write this equation. And you can see that linear equation as product of vectors. So let us say a set of simultaneous linear algebraic equation which we have seen before, a1 1 x1 a1 2 x2 etc. a1 and xn equals b1, a2 1 x1 a2 2 x2 up to a2 and xn equals b2 etc. am1 x1 am2 x2 up to am and xn equals bn. Now let us see the following vectors. One vector is this vector x. This is a column vector, x1 x2 etc. up to xn. Then a1 is a1 1 a1 2 up to a1n, a2 is a2 1 a2 2 up to a2n etc. etc. am is am1 am2 up to amn. These are all column vectors. That is why I am writing this transpose sign, because by default we take all vectors as column, and whenever we take row vectors we have to write that specifically. So this set, based on our definition of these vectors, we can write a1 dot x equals b1. This is a1 vector and x vector. This is a dot product of them. So a1 dot x equals b1. This is my equation 1. Similarly, a2 dot x equals b2. This is my equation 2, etc. etc. am dot x equals bm. So you can see every equation we can write in a short form here. Left hand side of every equation is basically dot of two vectors. This kind of relation between the linear equations and vectors are very important in linear algebra, and this is actually the starting point of the theory of linear algebra. But our purpose is not to go very deep in the theory of linear algebra. These are the basics we needed to know. We have to now think about how we are going to solve this linear equations, and in upcoming lectures we'll discuss that. So in summary, we have seen the distinction between linear and nonlinear equations, and we have seen the connections between vector and linear equations. For your exercise, you verify the linearity of the following equations. So check these equations are linear or nonlinear. We have two algebraic equations and two differential equations. So you have to be careful to check these differential equations are linear or nonlinear. Algebraic equation is simple. At least the second equation is linear, that you can clearly see. Other equations you have to think about it and figure it out, they are linear or nonlinear. So that's all for this lecture. Thank you, and I'll see you in next class.